Thank you very much. So thank you for this opportunity. And this is a talk that I've been wanting to pull together for a while. And so this seemed to be a perfect venue. I'd just like to note that this work that I'm going to talk about today has reflected a lot of different people, my students, postdocs and visitors, fellow faculty, and we have now quite a number of industrial collaborators. So the first thing I'd like to do, and one would think, given the maturity of this area, that this would not be required, is to try to sort through the terminological chaos. I see the same things referred to in many different ways. We hear about AI accelerators. I think the most common is machine learning accelerators, and yet we're talking about something that I would actually call a deep learning algorithm accelerator. And to try to give a little more context on this. So what I have here is the way the situation looks to me, which is we have this very broad notion of artificial intelligence. The definition is, some people would call it broad, some people call it vague, and it's always evolving, but basically has the notion that in computer software, we are trying to emulate in some way intelligence that we typically associate with human beings. Then a subset of that, I would say, is machine learning. And these are really just a family of data-driven algorithms rooted in statistics. And then within that, we have deep learning, which is actually a relatively small set of machine learning approaches, but one that has become very successful. I should note that, even I've discussed this with Stuart Russell, who's kind of the most one of our fellow faculty and author of one of the most successful artificial intelligence books. He's comfortable, I think, with this kind of Venn diagram or these intersecting elements. But Michael Jordan, who's one of the most published machine learning researchers, basically doesn't want to be associated in any way with artificial intelligence. But this is the way I look at things. So probably what's most relevant is I'm contrasting on the left here the notion of just an ordinary algorithm, a deterministic algorithm. So we all know what that is. We've all, probably most of us have written those. You deterministically define the behavior in software. You code it up in some probably imperative programming language, and you embody in that sophisticated algorithms for solving problems like sorting, satisfiability, and so forth. Now I'm contrasting that with supervised machine learning on the right here, where developers don't define precise behavior, they give a template of behavior. And then in the next step, they actually are trained, is required to be trained by data sets. So my group, beginning about 2007, did quite a lot of work in machine learning, and in particular, even then our focus was more computational. We were looking for ways to computationally or to accelerate the machine learning computations. And we did that across a broad range of application areas in computer vision, audio analysis, and multimedia. And frankly, we were fortunate to be pretty successful at doing those accelerated. We routinely accelerated applications by 10 to 55x over prior out-of-the-box solutions. And to get some sense of how it goes, I'm going to be using the example of image classification, where on the far left, we have an image, say, we observe that as a cat, and then we take that image and we run it first through a machine learning algorithm, which based on handcrafted features, extracts certain elements of that image and turns them into elements of a vector space. And then when we take these resulting vectors, we then classify the vectors using some sort of classifier, which would, in this case, be trained, something like a support vector machine. And this is something that we actually did, and this is probably our most successful work for that, work of that era, in which we developed a very fast support vector machine training and classification implementation, which ran on GPUs. And this was really, I think, Brian Catanzaro, who did this work, who's now vice president at NVIDIA, looks back on this, I think rightly, as the beginning of applying GPUs to accelerate machine learning algorithms. So just to give a sense of the diversity of algorithms that we explored at that time, for computer vision, here I have a long list, I won't name them all, as well as we did work on speech recognition and audio analysis. And the point that I'm trying to emphasize here is just the very broad diversity of different algorithms which we used and which we put together to achieve implement a single application. However, then in 2012, what I'm showing here is the top 5 error rate, so lower is better. And in 2012, there was a significant discontinuity in which the kind of progress that one might expect to be achieved maybe over 5 years was achieved in a single year as we moved from 2011 to 2012 with AlexNet, significantly reducing the error on ImageNet. And so with that, we began to see a new era of deep learning. And to compare supervised machine learning and supervised machine learning using deep neural nets, really the only difference is that this kind of broad class of machine learning algorithms, which I showed you before, are replaced by a single deep neural net. And this is something that we did. So we had already done image classification, as I mentioned before, as well as object detection using classical machine learning approaches, as I mentioned, using extracted handcrafted features and training a classifier. And the difference with a deep neural net approach to that, and what I'm showing below is our neural net squeeze net, is where the neural net actually over its first number of layers, learns the features. There's no particular handcrafting performed by humans in any way. It does all the learning on its own. And then it also learns the classifier. So the actual approach or the actual logic, so to speak, to do the classifier is all learned from the training examples. So it's quite a different approach. And the amazing thing for us, and again, I think to appreciate, you have to see that we've been working, as I say, for years on applying machine learning, and we felt quite proud of ourselves and our ability to figure out what was the right machine learning algorithm to use and so forth. And in the work that we were doing on computer vision, all the sophisticated use of machine learning algorithms that we used was being displaced by a single convolutional neural net. And then very soon, the kind of work that we're doing in speech recognition and audio analysis and so forth were all replaced at that time, by recurrent neural nets. So since about 2015, frankly, it took us a few years to really integrate the changes that were happening. We began to address pretty much the same applications that we had been looking at before, but we've been solving all those problems with deep learning. And in particular, I will reinforce that in a typical application, such as object detection, essentially that problem, which used to be solved by, say, 10 or 15 different machine learning algorithms, was solved by a single convolutional neural net. And what I show here on the far right are essentially the family of neural nets that have been successfully used to solve problems in those areas. Now, I want to pause, since we have this very unusual situation in which a kind of a single algorithmic paradigm has very, very broad applicability. So I think it merits really kind of digging into the nature of the computations associated with that. And what I'm showing here is kind of a pattern language that we had developed for parallel computation. One is looking at program structure. And among all the diverse program structures that are used in creating complex programs, basically deep neural nets use the simplest possible one, which is pipe and filter, which is principally just feed forward. Some input, like there's cat, is just fed forward through a series of filters. And what are shown in purple, and what are those filters? Those filters, if we look at them computationally, are basically just incarnations of either dense linear algebra or sparse linear algebra. So deep neural networks are, because of these linear algebra functions, are arithmetically intensive. And linear algebra, I think, is probably our most studied computational pattern. And moreover, it's quite striking because of this very simple control structure. It's very simple, and it's also static, and therefore these are statically scheduled. So if it's surprising that a single algorithmic paradigm would be so successful, what's even more surprising is that it's actually a fairly simple computational paradigm and statically schedulable. So basically, if you look at these characteristics, we have something, we have kind of an algorithmic paradigm, which is broadly applicable. It's very amenable to optimization because of static scheduling and because of the extensive use of linear algebra. And that's led to lots of academic papers on how speeding up these computations, lots of internal efforts inside of companies on speeding up these computations with neural net accelerators, and an unprecedented number of AI-centric hardware startups. And what I show here is just a popular kind of roadmap of the AI chips that are these are all real. Every single dot here is a real development of some chip that's particularly targeted to doing these deep learning acceleration. And again, we see the broad use of the term AI here when, again, I think every single one of these is actually focused on accelerating deep neural nets. Now, when I look at this explosion of activity, I believe I see what I would call this notion that if you build it, they will come. That is, we're going to create this computational capability in hardware, and then software developers will naturally be drawn to use it, and then they will create an ecosystem. And you know, now 40 years into my career, I know, well, actually, that doesn't always work out that way. On the left there, I see Stretch, which is kind of a relative of the Tensilica family, which does still exist, but these were packaged parts based on the Tensilica processor. And I remember this one well because I actually invested some money in this and lost it. All told, I think there were $38 million invested in that. And then an even bigger, I think, net loss initially was Tabula at $182 million. Both of those essentially unsuccessful chip projects. So what does it take to be successful? And can neural net accelerators provide that? And so I really haven't heard any more better words of wisdom than Dado Banatao. He's funded Tallwood Ventures out of his own pocket, and he was also co-founder of a number of chips, Mostron Chips and Technologies, and he's most famous for S3 graphics. And what he says is, to get customers to move from one solution to another requires at least a 5x improvement on some key metric. So that's the preamble to the talk today, which is essentially my point that I want to get across is, if you're an architect building a neural net accelerator, you need to know your applications better than your customers. You need to understand what are real constraints on accuracy, power, energy, and memory footprint. And you understand how optimizing to meet these constraints can lead to significant savings. You need to understand the strengths and weaknesses of different neural net models, architectures, and how to match them to that application. So you need to be very conversant with neural net models. You need to know how to optimize those models, and you need to, if you're providing a new piece of hardware, you need to provide libraries for that in the state-of-the-art software stack. And if you don't do this, then all the work you put into architecting your neural net accelerator will be overshadowed by these application and software issues. Now, depending on the time zone in which you're watching this, if you go, well, I knew that already, then you're welcome to take a break, because this is really all this is the essential key points of my talk. And if you already believe it, then you don't need to listen. If you're a little skeptical, or you at least want to see some of the particular constants, then please continue to tune in. Okay, so one of the first decisions to be made is the type of accelerator that we're looking for. And the broad choices there are cloud, in which you're probably focused on both training and inference, or client, which is inference primarily. And this may seem like kind of an pretty obvious distinction to make, and yet Uh, I see a lot of academic papers published in which they go through and they show the results table and so forth, and they never actually mention which of these two types of accelerators that their neural net accelerator is targeted for. And I think that's that there really should be significant architectural differences there. So let's first look at the cloud. And so every computation is we see is typically hosted either in processor, cloud, and client. And so let's look at the cloud. And the first obvious thing to note here is that, so what I'm showing here is starting in the lower left with a single TPU V3 socket, and then plugged into a board, then onto a rack, and then put in what's called a pod of TPUs, and then those pods, there might be, say, I think about 120 of them in a data center and so forth. And the cloud market is very attractive. So if you're thinking of building an accelerator, this would be a natural place to look. You know, each of those major customers below that I mentioned here is using literally millions of chips, and so it constitutes a huge market. And it's then not surprising, I think, that if we're looking at companies that are getting hundreds of millions of dollars to over $1 billion in venture capital funding, they're focused on this very large market. And we've already seen quite significant exits, one from Nirvana to Intel for 500 million, and then Habana to Intel for, I believe, $2 billion. Nevertheless, you know, one of the points that I'm going to be reiterating during this talk is that you still need to understand your workload. So what I'm showing you on the y-axis is the parameter count of a deep neural net model. That is, you kind of think of that as the weights, which are the various knobs for defining what that neural net model does, and which are those values are achieved by training. And on the x-axis, we see a timeline, and the initial focus of deep neural nets was in computer vision, and then natural language processing or understanding was next, and we see quite huge models there of 1 billion parameters. And you might think that was the largest, but then actually even larger are recommendation systems, which have literally can be the parameters that are trained can be in the terabytes or even tens of terabytes. Tens of terabytes mentioned, I believe, in an Alibaba paper. Okay, so that's pretty different. And then another thing that's pretty different across these applications is what's called arithmetic intensity. And so if you're not familiar with that, it's a very simple concept, which just basically says the arithmetic intensity of a particular algorithm is for a single operation, how many bytes of data do you fetch in the performance of that? And the notion is you want that to be higher. That is, you want to do fewer fetches and reuse that data as much as possible. So what I have here on the y-axis is the arithmetic intensity. So higher is in some sense better, or enables more reuse. And what I have on the x-axis here is the size of model and neurons. And you see that these are quite diverse workloads, and it's very challenging to architect an accelerator which will work across these broadly varying applications. And I have to say, you know, I watched the growth of this cloud-oriented neural net accelerators pretty closely from the beginning, and I didn't hear a lot of discussion of this issue in the development, or even a clear sense of which ones they were targeting. And here's another look at the same thing with a little bit more quantitative. So I've got the broad category of the application area, the types of models, size, the relative arithmetic intensity, and the maximum at any given time, how many activations are actually active in a particular layer. So, you know, if you want to go to sell to Google and so forth, you want to understand the distribution across these, because I'm claiming that they're different, and so you probably want to be really good at one and at least okay on the others. And this is some data from Dave Patterson, who's now retired from Berkeley and working full-time at Google, but he gave a talk at Berkeley. And what we see on the top there is the multi-layer perceptron, which is essentially used in recommendation models for inference and training. You see it's the bulk of the inference workload. RNN, which is now increasingly being evolving into transformer, and convolutional neural net, which is used in computer vision, and then finally transformer, which is increasingly using natural language understanding workloads. And so you see a pretty significant more recommended for inference, and in training we see pretty smooth across the different categories. Facebook, this is more recently released data from Facebook, and they have come out fairly clearly. Basically, this RMC1, 2, and 3, and so forth are all recommendation, different variants of recommendation. And basically, Facebook is saying that over 80% of their workloads are actually devoted to recommendation systems. So that's the workload that if you're attacking these neural net accelerators for the cloud, that's the workload that you want to go after. So I would say that the cloud market is very challenging to penetrate. So even though there's a centralized set of customers and a huge market, may be hard to crack because the incumbents, that is NVIDIA and Intel, are veterans of years of competition. Every one of your customers has internal efforts that will compete with you. Some of those are very visible, such as Google has already been successful with tensor processing unit, and I think it's now going into its 4th generation. Others are believed, and some are quite vocal, some are not. Some are vocal, like Amazon, some are less so, about their internal efforts. So that's going to be a challenge. And then finally, the processor is only half of the solution in a cloud or data center environment. And we see the relevance of that is Intel acquires InfiniBand company from QLogic for $125 million. They have since spun that back out of Intel, but they competed unsuccessfully with NVIDIA to acquire the networking company Mellanox. And I think the competition for these and interest in these companies is all due to the realization that if you really want to do well in cloud workloads, then you really need to be able to integrate very tightly with your networking. Okay, so I could go on more about the cloud and some of the challenges, but I really think that in some sense the challenges there are very significant, but they're also maybe even more business oriented. I actually think the client is more, I certainly find it more interesting. It's more where my expertise lies. So I'm going to focus on that for the remainder of the talk. And, as we move from even a single socket in the cloud to the client, we're taking a huge computational hit as we go from even in a single socket from 200 to 300 watt budget down to 1 to I would say 20 max. And so it's good to realize that thermal design point is one of the constraints. And so we might see up to 20 watts for some applications, but for most applications, I would say it's more like 1 to 7. Of course, that's essentially a chip packaging and a system constraint. And then I always point out that emphasize to my students that but there's also that power, lower power isn't exactly the same as lower energy for a particular application, and the lower energy is really more constrained by what you want to achieve with your battery life. So if you're looking to attack an accelerator for the client side of things, then you can see across here a variety of different products, ranging from something that you might attach to yourself, like with digital pedometer, all the way up to the laptop that you're using, and then probably from the middle of this down is probably what you're going to be targeting. And here's another look at the same thing. So what I have in the middle there is the different thermal design points that you might be operating in. On the far right, I'm comparing that to, say, an urban taxi as an extreme different, and then the labels across the top essentially say different markets you might be addressing at those different thermal design points. Before I proceed further and really begin to dig into the various things which impact the amount of acceleration you can get with the neural net accelerator, I do want to point out that on the one hand, if you look at something like the Apple A13, it's the neural net accelerator there outlined in orange is just 10% of the die size, but it does deliver the majority of the tops per watt in performance on deep learning workloads. So despite its relatively lesser silicon area, its impact on the speed of that chip is very significant. And the kind of cartoon level description of the architecture of a neural net accelerator is pretty common. They're a matrix of individual processing elements. Those processing elements are typically just a multiply accumulate unit with a register file, and then of course you have some interconnect of how they're connected. So in the remainder of the talk, so you decide you're going to build a neural net accelerator for the edge. And in the remainder of the talk, what I'm going to be doing is looking at this stack that I show on the left here, going from the application and its constraints through the neural net architecture, the neural net optimization frameworks, hardware, software co-design, and then all the way down to the hardware itself. And what I want to do is look at the particular impacts, basically how much is to be gained at each level. And we'll be going into that in some detail. So starting with application and constraints, and oh gosh, makes me feel old, but back in the late 80s and early 90s, I used to be on a lot of panels. Power was just beginning to be important there. And I was working quite a lot on logic synthesis, kind of devoting my life to it. And I would be on a panel with Bob Broderson, and I'd be saying, well, I can reduce latency and power 20% with logic optimization automatically, and so forth. And then it became kind of a joke. Bob would say, well, I can reduce latency and power 2000x at the application level. And so we'd get a chuckle out of that, and then we'd be invited to the next workshop to do the same show again. And I didn't doubt that Bob was right, but that so infatuated with logic optimization and so forth that it didn't deter me from pursuing what I was doing. And I point out to him, even after you get your 2000x, you're still going to want my 20% from logic optimization. Well, I'm very happy now to be more engaged in the application side of things, and I'll mention for I guess now the third time that we're working across a broad range of applications in vision, audio, natural language processing, understanding, and multimedia. And our first successes in applying what we call our squeeze approach have been to various computer vision problems. These are pretty standard problems. So I'm showing here image classification. Simply given an image, what is the predominant object there? Then there's object detection, in which you want to identify each individual object in that. So the classification we approached with SqueezeNet, which was kind of a breakthrough net in terms of showing what you can do in a very, very small model that could be deployed at the edge. Then we worked on object detection and finally semantic segmentation. All these are very relevant to autonomous driving, and that's something that we went on to build a company in called DeepScale. And DeepScale was ultimately sold just a couple of years ago to Tesla. And we focused on advanced driver assistance systems and autonomous vehicles. But as a small startup, you get a lot of knocks on your door saying, well, gosh, we might be interested in your company helping us with our mobile robot, with our drones, with our surveillance systems and so forth. So we got exposed to a lot of different applications there. And one of the first things we encountered was The very recurrent is that, we want to get, the customer would say, we really want the top accuracy. ImageNet is out there, so we really want to peg these ImageNet numbers. And, being very familiar with ImageNet, we were a little puzzled by that. In ImageNet, of the 1,000 classes, there are 122 different dog classes that you need to get precisely correct to get a good ImageNet score. And about the only application we could imagine of that was some sort of iPhone dog identifier application, which is not what people were approaching us about. In particular, from an autonomous driving standpoint, the same dog classes are kind of like just one, just to even identify that that's a dog and not something else, not a fire hydrant or something. That's about as much as you want. So you have one dog class, and if you confuse a golden retriever with a golden lab, that really doesn't matter. So that, I actually think, very broadly, because, and probably it's not so amenable to academic work because it's so application dependent, that looking at application by application notion, what does accuracy really mean here, is, I think, a very fruitful area. So accuracy is one thing which I think if you want to be successful in application, you need to think carefully about that. Another one is just what kind of resolution do you need? Again, I'm talking about particularly about computer vision, which is where we get started. So what I'm showing here is the typical kind of normalized resolution in the ImageNet image, which you crop down to is, or reduce down to, is 256 by 256. And we see that there's 126x difference in that between that and, say, a Ultra HD 4K camera, which is not exotic at all in terms of computer vision. And what I'm pointing out here is, for a single computer vision problem such as object detection, we can see very different constraints on the resolution required, the speed, and accuracy. And so at one extreme, if you're trying to do a driver assistance system or autonomous vehicle, which is going to operate in the highway, you probably want that to go at a full 60 frames per second and be able to process that in real time. You want to be able to do high definition camera, and you want to get the highest accuracy scores that are possible. At the other extreme, if you're trying to do the same, in some sense, the same object detection problem, you're trying to just identify how your customers move, say, through a supermarket. You're just trying to find traffic flow and optimize that and look at how sales are related to the traffic flow. Well, then you can probably go all the way down to 1 frame per second. People are not moving very fast. To identify a person relative to, say, a shopping cart is not so tough. So you can probably get by with a 256 by 256 image. And in terms of accuracy, here I'm saying like accuracy in terms of an object detection benchmark, or like COCO, or your score on that may not be so great, but it still may be, your object detector may be fine for your particular application, identifying individual people in your store. And then somewhere in the middle is something like a campus delivery autonomous vehicle, which is also not moving very fast, but it's moving more consistently fast than, say, human in a supermarket. So you might be up to 5 frames per second. You want to be able to identify, different characteristics of terrain. So you need a bit better resolution in your camera and some mid accuracy. But as you can see from this example, we're really seeing, if you kind of multiply it all out, a 7,000x difference in key computational parameters of speed and throughput in these different applications, all of which we might call object detection. So that's all on the table. Another application area that I'll be going back over is speech recognition, natural language understanding. So what I'm showing here, going left to right, is we're talking about a system in which you take voice input, you turn that into a sequence of words, like, so you get where are bananas, and you actually get that into the word sequence, where are bananas, and then you You use natural language understanding to understand the intent, which is to find some location, the entity, which is bananas, and the answer is IL1, and then you output the word sequence IL1. And then you don't want to just display that on screen. You actually want some voice output of IL1. And so I'm just showing across the bottom here work that we've used on various aspects of, we have worked on all aspects of this problem. And in terms of application characteristics and their differences, what we see here is the fact that the amount of language coverage that's required here is dramatically different between these home and personal assistants and another one such as menu ordering or service kiosk. Your personal assistant, you want full vocabulary, but you certainly don't need to do a full vocabulary to pull up to a Burger King and order from a menu, or if you go to a question kiosk, say in a little shopping or supermarket, to ask questions. And so what I'm showing here is just turning that observation and making it somewhat quantitative. So what you see across the time is across the y-axis, the amount of computation time required, and what you see across the x-axis is number of vectors, which you can kind of think is just a proxy for the language size. And you can see it basically grows, that's a log scale, it's growing exponentially with the number of vectors. And so you can see a 1000x speed up, depending on going from very limited vocabulary to full vocabulary. And I'll give a hat tip to Bob Broderson. This is what he was trying to tell me many years ago. All right, so we're just getting started. What I'm doing here is pricing out. If we look at latency, energy, and memory, we can see easily there's factors of 10 to 1,000 in latency, 10 to 1,000 probably in energy as well, and 10 maybe up to 100x in the memory required to perform this deep learning application. And we can make that numbers because we want some of these natural language understanding models are getting to billion of parameters. So we could say 100x, 1000x, we could even say 1,000,000x differences in some of these emerging natural language understanding models, but more realistically, let's say 10 to 100. Okay, then that's application and its impact. And now let's look at the neural net architecture itself. So we learned, and I think we were probably among the pioneers of the notion that while most of the field was looking at larger and larger models for computer vision to get better and better accuracy, we were actually interested in the edge and trying to get by with very, very small models. So simply by doing manual exploration for the simple image classification problem that I discussed before, we were able to get the same as this breakthrough net, same accuracy, top 5 accuracy of this breakthrough net AlexNet with an actually reduction in 50x in the model parameters. And then that led to more and more publication of work looking at this problem of efficient nets for the edge. And what I'm comparing here, particularly accentuating YOLO v2, which is a very popular net for object detection, to MobileNet v2 plus SSD Lite. And we're seeing factors of 12 in the number of parameters and factors of 20 or more in the number of operations per image, difference between those. We now have many excellent model families for the edge. Our Squeeze family, over these last years, we've collaborated more and more with Facebook to produce the Facebook net family of nets, which is now in its 3rd generation. Andrew Howard and folks at Google produced the MobileNet family, and Song Han has done a lot of good work at MIT. And this is Song Han's slide, actually, that I stole from him. And what I'm looking across the top here is we have computation. It's nicer to look at throughput or latency, but we use just the number of raw computations max as a proxy. And what we see is with comparable accuracy, we may have a model which is actually 14x less in terms of computation, and that's his once for all net relative to exception. And this is a bit of an eye chart, but it's what you look at it is we're just looking at a range of accuracy across 5 or 6% here, and what we're seeing is like hundreds of difference in terms of the latency to actually to achieve those accuracy. And that was computer vision. And now looking at, again, I want to keep going back and forth to natural language understanding. What I'm showing here is if we compare reformer to linear transformers, you have speed, that is examples per second across the x-axis, and the accuracy score, this long-range arena score on the y-axis. So we look at two nets with the same accuracy, reformer and linear transformer, and we see a 5x difference in the throughput. Here's some work that we did, and we're comparing our squeeze BERT to a BERT-based model, to mobile BERT, which had particularly been targeted for the edge, and then our squeeze BERT, where we saw we were able to get a 4.3x relative to BERT-base in terms of speed up, and about 1.4x relative to mobile BERT. And here, just going quickly through this, we for natural language understanding, we have across different net families, we have 14x differences in latency and 4x in memory, although we are losing some accuracy here in some of the very small nets. So looking at neural net models here, I showed you a lot of different numbers, but it's very easy to kind of justify a 4 to 50x in terms of differences in latency with comparable, well, at the low end of that, 4x, say, at least, keeping more or less the same accuracy, and up to 50x if you're able to go, say, 1 or maybe up to 4% degradation accuracy. And again, the accuracy for your application may be very, very different. So you may be meeting your application constraints, even though relative to a standard benchmark, you're getting less accuracy. So next, let's look at neural net optimization. So again, we learned this as early as SqueezeNet, that was 5 years ago, that after using original model design, just kind of head scratching and design space exploration, we were able to get a 50x reduction in the model size. And then we worked with Song Han and his advisor, Bill Dolly, at that time Song was at Stanford, to get another 10x, an additional 10x to compress that model down all the way to 500 kilobits. So let's talk about that. So in my group, our workhorse for optimization, so in this case, we're keeping the net constant. We're not actually changing the neural net model or the neural net architecture. We're just trying to optimize it. And one standard optimization is to try to, for your weights and activations, to go from 32 bits, perhaps to 8 bits, 4 bits, or even down to 2 bits. And so you're essentially taking some continuous number and quantizing it down to a particular small bit quantity. That gives you less memory footprint, faster inference, and kind of pricing that out. To understand that, this may be a different way of looking at the figure, but I'm sure all of you have seen this figure, which is comparing, say, an 8-bit add to a actually 32-bit DRAM read, and just showing the significantly greater 640x, or 640 in absolute picojoules of a DRAM read versus the very small number for an 8-bit add. So the point is that memory accesses are your highest cost. And so if you reduce the size of what you're accessing, you're able to access more with it and reduce the memory access cost overall. So this is some data from NVIDIA, which is looking at, as we go on the far left here, from different numerical representations of floating point 32 all the way down to int4 and even int1. We see here the throughput increase, say going up to 32x, the memory reduction of 8x. And here's another look at how quantization produces lower latency. So looking at batch size 1 of MobileNet versus Inception v4, we're getting across these nets, increases of like 4.4. And if we can batch things up a little bit, we can even do better up to like 7x. Here's some of our own work. This is from one of our Hawk papers, where we're showing even if you got 8-bit, which is a pretty aggressive quantization, if you can reduce that further, as we've done across a broad range of applications, you can get another additional, in addition to whatever you got with your 8 going to 8-bit, you get an additional 1.45x in latency and 1.8x reduction in memory. So here's work that we did on those were prior work I discussed was on quantization for computer vision. I want to keep looking at natural language understanding to show how these concepts are not local just to computer vision. And we showed how using a net for version of the very popular BERT transformer architecture, we want to get a 4x reduction in model size, a 3.1x improvement in latency, and about we estimate a 16x reduction in power. Now, natural language understanding, there are other techniques which are successful. Pruning, and I don't have time to talk about precisely what pruning is, but pruning is another optimization applied, and you can see in there factors of 2 in size, latency, and power. And then another optimization is distillation. And here again, we're seeing model size 1.6 reduction, somewhere in latency, and about 2x in power. So pricing all that out, the numbers are coming down here, but still they're significant, where we can rely on optimization, I think, relative to an optimized model to get us another 4 to 7x in latency, 4 to 16 in energy, and 4 to 8 in memory. So moving on, then we want to look at frameworks, and I'm presenting here essentially an NVIDIA kind of software stack in which we have standard frameworks such as PyTorch or TensorFlow at the top, and then those on top of those are built on top of cuBLAS and CUDNN, and those are built on top of CUDA, both individual kernels and runtime. And then here are some of the different linear algebra, or different libraries associated with NVIDIA. And one is cuBLAS, which is the basic linear algebra subroutines. That's a key one for most deep learning. And then these can then be integrated in with other frameworks. And just to get a sense here, what I'm trying to show is you're a neural net architect, and you've got to provide libraries for your architecture. You're not getting those for free from anyone. So if you just try to do something naive, like just turn it into an optimized matrix multiplication, but still matrix multiplication, you're losing, say, a factor of 3 there. And if we look at this is essentially reiterating the same point. It's easy to get a 3x speed up by moving to direct convolution, even with you have a great matrix multiply operation. And then this is going much finer into the CUDNN library and showing how we depending on the particular nature of the convolution that we want to do, say a 3x3, we can easily get another factors of 5 or 6 in terms of latency and memory reduction. And then this is from the TVM group showing their improvements relative to hand optimized. So all these are optimizations in the software and in the libraries that we might expect to see from our framework. And so I think it's easy to argue we can get factors of 3 to 10 in both energy and operations, and even perhaps even more in memory. Okay, and now moving further down the stack to hardware software co-design. And so I'll just kind of flash at you that this is very early work that we did, but you're getting some sense here. It's a log scale. and so here's a good example for co-design, which is it's the software and algorithms which enables your reduction of bit precision, and that's on the software side. But once you're given that reduction precision and you're able to go down, say, to 8-bit or 4-bit, what I'm showing on the y-axis here is the increase in number of tops per watt that you're able to achieve. And so that's essentially because you're able to size down that multiply accumulate unit, which is the core element of your neural net accelerator. And another thing that we've explored is the going not just quantized from 32-bit down to N4, but also going from floating point generally to integer. And it's easy to see how I'm comparing here a 32-bit fused multiply accumulate down to simple N4 integer multiply accumulate, which uses 24x less gates, which is, let's use that as a proxy for power. So that all prices out to where we can, I think it's easy to convince yourself you can, with co-design, careful integration between the hardware and software, you can get a factor of 2 to 20 in latency as well as in energy, and probably 4 to 40 in the actual, not memory. We're not talking about model parameters here, but actually silicon area. Then finally, this is your number as potential neural net architects or people interested in that area, not mine. But I think probably if we normalize things in terms of pure kind of low-level hardware architecture and microarchitecture implementation, maybe there's 2 to 10x on the of latency on the table relative to someone else's good implementation, maybe 2 to 4x in memory. So reviewing that in context, I'm looking here just at, all right, let's say that you have a very conservative situation. Your customer says that they're going to choose the application constraints, like frames per second. They're going to choose the neural net model. You're not going to choose that. Okay, even with those other elements frozen, it's easy to see how you can get a factor of 12 to 70 between neural net model optimization and frameworks. And I'm trying to argue here, that's on the table here. If someone else exploits it and you don't, it doesn't matter that you're doing better in your hardware architecture, because you're going to lose all that in competing with their software environment. If we go a step further and you can relax accuracy a little bit and change the neural net model, then we can easily get your so they're going to freeze the application constraints, but you get to relax the model, then you can get factors of 48x to 100x or more there. So I've been talking about this as kind of though you're, what you could possibly lose. What I like to flip that around and say there's a tremendous opportunity here is if you can get all these different aspects of the application and software stack lined up, it's easy to imagine that you're able to get a factor of 10 to 100x over a downloaded popular neural net and run it on some unoptimized and some popular hardware. So I do want to, just to wrap up here, I want to mention, I always like to say, okay, in typical academic style, I went really deep on one portion of the problem, and I would say that neural nets are at the core of the solution. Many deep neural net, many of the different applications I described, but there's much more to an application accelerator than just the neural net accelerator architecture and its supporting software stack. So, for example, in an ADAS solution, if you're actually trying to produce a chip, you may be surprised to hear that they want a neural net accelerator, but on that same chip, they wanted to run the infotainment system and other in-cabin and passenger functions. The images that you use may in fact need on-chip pre-processing, and they're expecting your chip to do that as well. And then of course your chip has to get data efficiently on and off and support many different interface protocols. And so we point out here a company that I enjoy working with, SimAI, which is, I think, doing a good job of holistically looking at the constraints in terms of supporting a wide variety of interfaces, support for for compression, decompression, optimization of images, as well as providing general CPU support for a variety of housekeeping and infotainment functions. Okay, so as an architecture, if you can, putting things positively, if you can know your applications better than your customers, understand the real constraints on accuracy, power, and energy, and the memory footprint, understanding how optimizing to meet these constraints can lead to significant savings, understand the strengths and weaknesses of different neural net models, architectures, and how to match them to an application, master neural net model optimization, and provide libraries in the state-of-the-art software stack, then you can produce a superior state-of-the-art solution. You can really outclass your competitors. So in summary here, I would like to say thanks to my research group depicted here, and also thanks to my sponsors. And I'm very happy to take questions now. I think we started a bit late, but I think I'm in my talk just pretty much right on time.